So, hello everyone. I'm welcome to the live section for this course, which is Physics of Linear and Nonlinear Optical Waveguide. So, I'm Gitanjali Jaina. I'm a scholar from IIT Delhi. So, basically, in this week, we have seen what is optical Kerr effect, and how does the this effect how does the electromagnetic wave propagation, how does this get affected by the Kerr effect, how does the envelope look like, and how the instantaneous frequency or phase or refractive index, how does this change under the core effect of this optical fiber. So we have seen in the earlier class that the Chi2 effect is not there for the optical fiber because it's a centrosymmetric material. So the dominant nonlinear effect for the optical fiber, it will be core effect because of the Chi3 component. So we'll see problems related to that, which will cover whatever the concept is there for week 11. So let me start. We'll start from first question. It's so the question says the nonlinear polarization in an optical fiber. It's given by P0, P is epsilon 0 chi 3 E3. Assuming that the incidence of wave at frequency omega 1 and omega 2 with propagation constant B1, B2. Obtain the expression for nonlinear polarization at frequency omega 1. So we have two frequency the incident source have two frequency component. One is omega 1 and one is omega 2. This is propagation constant beta 1 and this is propagation constant beta 2. And the question asks to find out what is the PNL, the nonlinear, the polarization, nonlinear polarization corresponding to frequency omega 1. Okay, so let me start. So you can write total incident field, you can write it as a linear combination of the two component. One is for omega 1 and one is for omega 2. So total electric field, it's a linear combination of omega 1, E1, E1 cos omega 1 t minus beta 1 z plus E2 cos omega 2 t minus beta 2 z. So in the previous live session, we have what we have done. We have just taken the cube of this electric field vector, and we have expressed it in terms of cos only. But for this, for this problem, I will uh, give a totally different approach. Like we can take also the exponential form to find out what is the nonlinear polarization. So this, if you recall, this is nothing but the real part of E1 e to power I omega 1 t minus beta 1 z. And this is also, this you can equally write it as, it's the real part of E2 e to power I omega t minus beta 2 z. So this form, this is also equivalent to half of E1 e to power I omega 1 t minus beta 1 z plus E1 star e to power minus I omega 1 t minus beta 1 z. This thing I think you already know. It's the real part you can express in terms of this. Similarly, we have an expression for E2 also, which will have half E2 e to power I omega 2t minus beta 2z plus E2 star e to power minus I omega t minus beta 2z. Okay. For the nonlinear part, we need the cube of this total electric field expression, which is epsilon q, chi q, and EQ. So this means, we don't need to express all the, so it has sorry, the third power of electric field, right? So that means it will have more components, more expression of omega 1 cross terms, same terms like this. But we'll typically focus on the terms which will have omega 1 because that is what the question is asking about. So that is why let us see first what is EQ. So EQ will come around 1 by 2 to a Q, which is 1 by 8. E1 e to power I omega 1t minus beta 1z plus the complex conjugate, which is e to power I minus I omega 1t minus beta 1z plus E2 e to power I omega 2t minus beta 2z plus E2 star e to power minus I omega 2t minus beta 2z. So let us say this is A. So we have a power 3 also. So first we can take it as A and second we can take it as B. So that means EQ will have 1 by 8. This is A plus B to a whole cube. So that means AQ plus BQ. 3A square B plus 3AB square. So we will not go into details of what is the total expression of AQ, BQ, and 3A square B and 3AB square. So we'll just see which component have omega 1 and we'll just write it. We will just write the total expression for that component. Okay. So we need to find the terms. Okay, so let me first write what A will be E1 e to power I omega 1t minus beta 1z plus E1 star e to power minus I omega 1t minus beta 1z. B is also same, but in place of E1 we have E2 and omega 1 we have omega 2. Okay, so let us see the terms which will have omega 1 component. So let us see whether AQ will have omega 1 or not. So AQ means AQ is, if you see, it has two components, two terms. So this means this will itself give A plus B to our whole Q. So which will have expression like AQ plus BQ plus 3A square B plus 3AB square. But AQ term, it will give 3 omega 1 or 3 omega, sorry, it will give 3 omega 1. BQ also, BQ means this to power whole Q. This will give 3 omega 1 and 3A square B. So for A square, so A is here, right? A square will get 2 omega 1. B will have minus omega 1. So that means we'll get a term omega 1 if we take 3A square B. So that means in AQ, we will have 3 A square B e to power I omega 1 minus beta 1 z plus, if you take 3a square b also, we'll have a component of omega 1, right? So we'll have 3 a1 square b e to power minus I omega 1 t minus beta 1 z. Okay. So in AQ, we have two terms which has omega 1. Let us see for BQ. So BQ means this term which has component, which has a frequency in terms of omega 2. That means it won't have any terms which will have omega 1 component. So that is why this will have no term having omega 1 component. Let us see 3a square b. So 3a square b, it will have, so this is A and this is B, right? So if you see A square, if you take the A square components like this, it will have term with both omega 1 and omega 2 that we don't want because it's 3a square b. So uh, it is like e to the power I omega 1 t minus beta 1 z plus E1 star e to power minus I omega 1 t minus beta 1 z. So we have to take a square multiplied by b, which is e2 e to power I omega 2 t minus beta 2 z plus e2 star e to power minus I omega 2 t minus beta 2 z. So in the first part, we'll have 2 omega 1 terms, but it will be get multiplied by with these terms which have omega 2. So that is why this term also, they don't have any omega 1 component. So no omega 1 component for 3a square b. So let us see 3ab square. So instead of a square, we have b square. So b square will have component in omega 1 because, so if you see b, the term b, it will have term like 2 omega 2, right? For a square plus b square. But the component which will have 2ab, so it will have 2ab term. So for 2ab, these powers, this power will cancel. So that is why we'll get a term which will have DC term, that is no frequency component. So this term will give E2 square. Okay. So that is why for 3ab square we'll have term like this part will have no omega, and from a part we will have a omega term. So what I mean is we have 3 a is E1 e to power I omega 1 t minus beta 1 z plus E2 star e to power minus I omega 1 t minus beta 2 z. This is A. And from B, I'm taking only the term which have zero frequency component, which is E2 square. Okay, this will be 2E2 square, like 2AB. So that is why it is 2E2 square. So this will give 6 E1 E2 square e to power I omega 1 t minus beta 1 z plus E2 star. Sorry, this is E1, right? So there is a typo here. This is E1. So E1 star E2 square e to power I minus I omega 1t minus beta 1z. Okay. So now we have all the terms which will have components in omega 1. So let us combine all the terms. This is the term we get here, and there is one term we get it. So that means only these terms is giving omega 1. So EQ will be for omega 1, it is 1, sorry, summation of 1 plus 2. So that means P will be P nonlinear polarization for omega 1. It's epsilon naught chi 3 by 8. So let us see the two term is, this is the second part. So this is 3 E1 square E1 e to power I omega 1t minus beta 1z plus 3 E1 square e to power minus I omega 1t minus beta 1z plus 6 E1 E2 square e to power I omega 1t minus beta 1z plus 6 E1 star E2 square e to power minus I omega 1t minus beta 1z. Okay, so these are the second terms are nothing but the complex conjugate of the first term. So you can simplify it further by writing this is equivalent to epsilon chi cube by 8 3 E1 square plus 6 E2 square E2 square E1 e to power I omega 1t minus beta 1z plus the complex conjugate part. Okay, so this is how we can filter out the terms, the uh, the contribution of omega 1 or some frequency or difference frequency or whatever the question is asking about for the nonlinear polarization. Okay. So let me move to the second question. Do you have any doubt in first problem? Because it was a bit long. So let me know whether you have doubt in any of the steps. So the question may seems a bit lengthy, but if you okay, if not, look, okay, let me go to the second question then. Please go through the question once. It says consider an optical fiber with N2 3.2 into 10 to the minus 20 meter square per watt. So N2 is given to you. And the effective mode area is also given, which is effective 50 micrometer square. If we couple 100 milliwatt into the fiber, obtain the change in the refractive index in the fiber due to the nonlinearity. This is the first part. In the second part, what we have, if we propagate a distance of 20 kilometer in the fiber, obtain the change in phase due to the nonlinearity. Assume that the wavelength of operation is around 1550 nanometer and neglect any attenuation inside the fiber. So first you need to find out what is the change in refractive index due to the nonlinearity. So fiber don't have any chi2 component, so that means the dominating term will be the chi3 term, which is Kerr effect. Okay. P is also given, which is power 100. This is easy if you recall the whatever derivation is already being done in the class, then you can easily find out. Because for the fiber, whenever there is a nonlinearity, we have change in the refractive index, which is the refractive index, you can write it as N0, which is without nonlinearity, what is the refractive index term, plus N2 into I. So this is the change in the refractive index, which is N2 into I. So N2 is given. I, you can calculate it because power is already there. It's already given. So it is nothing but N2 P by A effective. So N2 is given, it is 3.2 into 10 to the minus 20. Power is already given, it is 100 milliwatt, means 0.1 watt. And A effective, it is 50 micrometer square, which will give 10 to the minus 12. So this will give a value 6 into 10 to the minus 11. So this is the change in refractive index, which is a straightforward answer. For the second part, it was asking about what will be the change in the phase after covering a distance of 20 kilometer in the presence of nonlinearity. So the change in the phase, it is nothing but delta beta into L, right? The change in propagation constant into the total distance covered. Delta beta, you can write it as K0 into delta n multiplied by L. So K0 is nothing but 2 pi over lambda 0. Delta n we already know and length is already given. Okay. So all of the terms are already given. Lambda 0 is 1.55 micrometer. Delta n is 6 into 10 to the minus 11 and length is given 20 kilometer. So this will give a value of 1.555. So this problem was a relatively straightforward problem. So I think this problem will be, you don't have any doubt in this problem. So let me move to the third one. Go through the question once. It's a relatively easier than the first question. First question, we have two frequency component, both omega 1 and omega 2. But here we have only one frequency component, which is omega 1. Omega. So question is consider an incident electromagnetic field. It is given by EZT as real part of A0 e to power I omega t minus kz. What is the correct expression for the nonlinear polarization term oscillating at the third harmonic frequency? Third harmonic frequency means 3 omega, right? So you need to find out the terms which is corresponding to the third harmonic frequency. So this you can write it as we have seen before, this is nothing but E0 E0 e to power I omega t minus kz plus E0 star e to power minus I omega t minus kz. This we have already seen in the first question. Now we just take the third power of this electric field and need to find out what is the components. So EQ will be 1/8 E0 e to power I omega t minus kz plus E0 star e to power minus I omega t minus kz to power whole cube. So this will give AQ 3I omega t minus kz plus BQ e to power minus 3I omega t minus kz plus 3a square b 3a square b. So this will give a term of omega, not 3 omega plus 3ab square. E to power minus, so this will give a minus term. Okay, so that means this term we are not interested in this term. This term also because the question was asking about what is the frequency component corresponding to what is the nonlinear polarization corresponding to third harmonic generation. So that means only this term will have the nonlinearity because of the third harmonic generation. Okay, so we have EQ 3 omega. It will be 1/8 E0 Q e to power I 3 omega t minus 3 kz plus E0 Q e to power I minus I 3 omega t minus 3 kz. So finding the polarization is easy. You just need to incorporate these two terms. Okay. So PNL 3 omega. So epsilon chi q by 8 E0 q e to power I 3 omega t minus 3 kz plus the complex conjugate part, which is E0Q e to power minus I 3 omega t minus 3 kg. Okay, so let us move to our next problem. Go through the question once and try to solve it, because I think this is also it's related to question number 2. So if you know the formula, you can find out. So try to solve it. Okay, let me read out the question first in case it's not visible. So there is a Gaussian beam with power of 150 microwatt. So power is given 150 microwatt. Propagates in a single mode optical fiber with mode field diameter of 6 micrometer. Mode field diameter is given of the spot. It is also given the nonlinear refractive index coefficient, which is N2 of this fiber material is 3 into 10 to the minus 20 meters square per watt. Then the question is asking about calculate the change in refractive index due to the optical Kerr effect. What is delta N? If we recall, we have seen N because of the nonlinearity, we can write it as N0 plus N2 into Y, which is nothing but delta N. So try to find out what is the value of the delta N and let me know. I already know this is nothing but power by A effective. Power is already given, it is 150 microwatt. So you just need to relate what is the relation between A effective and the mode field diameter. (15.9 into 10 to the minus 11). Yes. Yes, it's correct. So that means we have you must have used A effective is it's pi MFT square by 4. So this is the relation that you already know. So that means delta N is N2 by I. Sorry, N2 into I. So N2 P A is pi MF D square into 4. So 4 into power is 150 and N2 is 3 into 10 to the minus 20. 5 into 6 micrometer. square, which will give 36 10 to the minus 12. So this will come around 15.9 into 10 to the minus 11. Okay. Okay, that means this can be solved by you. So let us move to our next problem. So there is a continuous wave laser with 300 microwatt of power propagates in a dispersion shifted fiber with the following parameter. So we have power 300 milliwatt. It's propagating along a dispersion shifted fiber with N2 is 5 into 10 to the minus 20 meters square. Fiber length is also given. It is total length of 10 kilometer. The effective mode area for this fiber is 50 micrometers square. And due to the Kerr effect, the refractive index changes, inducing a nonlinear phase shift of delta phi n. So calculate the intensity of the propagating mode in the fiber. So let us see step by step. So first is to calculate the intensity, which is easy, right? Because already the power and the effective mode is already given. So I will be E by A effective, which will be 300 10 to the minus 3. Effective is 15 to 10 to the minus 12. So this will come around 2 into 10 to the 10. So this is for the intensity, which is more straightforward. In the second part, find the refractive index change, delta n, caused by this Kerr effect, which is also you can easily find out, right? Delta n is nothing but n2 into I, which is already being calculated. So n2 it was already given 5 into 10 to the minus 20. I is 2 into 10 to the 10. So this will give a value 10 to the minus 9. So delta n is also easy to calculate. In the third part, find the nonlinear phase shift delta phi NL accumulated over the fiber length at lambda is 1550 nanometer. So we need to calculate the accumulated phase. So this we have already seen before. This you can write it as delta beta into L. So one of the expression for delta beta is we have seen in the class. It is gamma into P L, or gamma is nothing but N2 K0 by A effective into PL. So that means this is nothing but K0 N2 P by A effective into L. So this is K0 delta and L. So in the first question, we have directly assumed this is K0 delta N into L. But you can see here also, these two expressions are equivalent. So you can, if delta beta is given, you can directly calculate the phase shift using this formula. Or if not, then you can use this formula to find out what is the phase shift. So K0, it is nothing but 2 pi over lambda 0 delta n L. So let us put the parameters. 2 pi delta n is 10 to the minus 9 and total length it was given, I think 10 kilometer, so which is 10 to the 3, and lambda 0 is 1.55 into 10 to the minus 6, which is nothing but 12.95. Okay, so just remember only this formula. This is delta beta into L, or gamma PL, or K0 delta N L. You can see here, so in the last part, it was asking, evaluate whether the phase shift is significant enough to ensure the self phase modulation induced spectral broadening. So for that, what we need the condition that this delta phi, it should be much greater than 1, so that this the SPM based, the self phase modulation based broadening will be significant, right? So if you have already seen in the class that whenever we have a car effect, we'll see a chirping inside the pulse. So in the first part we have lower frequency, then as we move away from the center, the frequency increases. So for this to happen, we need delta phi much greater than 1. So here this is 12.9 into pi, which is much greater than 1. That means we can see a SPM based broadening. Okay. Okay. So let us move to our next problem. The question says, consider a nonlinear optical medium with non-zero chi2. In the process of some frequency generation, what is the correct expression for second order nonlinear polarization when the incident electric field has the following expression? So we have seen for in Chi2 effect, we have seen some frequency generation, and we have also seen difference frequency generation, which is omega 1 minus omega 2, or the DC terms, which is no frequency component. But for our problem, we'll basically focus on what is the term corresponding to some frequency. Okay. Uh, Let us start. So ET, it is the process is same. You just need to find out the power and separate the terms which will have the sum frequency. So this electric field, it is already given. So as we used to write before, we can express this as real part of E1, it were I omega 1t minus k1z plus real part of E2, it were I omega t minus k2z. This is half of E1 omega 1t minus k1z plus E1 star, it were minus I omega 1t minus k1z plus half E2, it were omega 2 t minus k2z plus k2 star e to the power minus I omega t minus k2z. And for the second order nonlinear polarization, we have P, which is the nonlinear polarization P is epsilon naught chi to A2. So E2 will give, E2 means square of this. So we'll have 1 by 4 term A, this is B, A plus B whole square. So what we need the terms which have omega is omega 1 plus omega 2, which is nothing but the sum frequency generation. For this, what we need, let us see, this is giving E square is giving 1 by 4 A square plus B square plus AB plus B, which is nothing but 2AB, right? So let us see term by term whether this term has some frequency generation or not. For A square, so if you see, A is nothing but, okay, let me write it here. So A is E1 omega t minus K1z plus A1 star E2 minus I omega 1t minus K1z. So A square will give the terms, if you take the square, this square will give 2 omega 1, which we don't need. And this will have a component for 2, for 2a. So the square will give 2a, right? So this phase will cancel. So we have a DC term, which is amplitude A1 square. So that means A square has no some frequency generation. Let us see B square. So similar to A square, for B square, we have B is A2 e to the power I omega t minus K2z plus E2 star e to the power minus I omega t minus K2z. So B square, it will give a term with 2 omega 2 and a DC term which have amplitude E2 square. So that means this term won't contribute. For AB, let us say for AB. So if you multiply A with B, we want omega 1 plus omega 2. That means this, if you multiply this first term with the first term here, so this will give a omega 1 plus omega 2 component. So that means we have now E1, E2, e to power I omega 1 plus omega 2 p minus K1 plus K2 z, right? Okay. And for the next term, this if you multiply the first term with the second term, this will give omega 1 minus omega 2, which is difference frequency generation. This we don't need. And if you multiply this term with the first term here, this will also give omega 2, omega 1 minus omega 2. So this we also don't need. And if you multiply the second term with second term, this will give a omega 1 plus omega 2 component, which we are interested. So this is E1 star, E2 star, E2 are minus I omega 1 plus omega 2 T minus K1 plus K2 Z. Okay, so AB is giving the terms we are interested. For BA also we'll see same type of expression. So if you multiply B with the first term, we will get E1, E2, E2 are I, omega 1 plus omega 2, T minus K1 plus K2 Z. And if you multiply the first term with the second term, this will give omega 2 minus omega 1. This we don't want. And now for this second term, if you multiply with the first term here, this will give omega 1 minus omega 2, which we don't want. And for the second term, we'll get a some frequency generation. So this, so that means BA and AB, they are giving the same contribution term. I omega 1 plus omega 2 T minus K1 plus K2 Z. So now we have PNL omega 1 plus omega 2 for some frequency. This is epsilon naught chi 2 E square for omega 1 plus omega 2. So this is nothing but epsilon chi 3 by 4 2 E1 E2 e to power I omega 1 plus omega 2 T minus K1 plus K2 Z plus the complex conjugate part, which is E1 star, E2 star, E2 R minus I, omega 1 plus omega 2 T minus K1 plus K2 Z. So this is the answer. Okay, I think this will be also clear to you because it's quite similar to what we have seen in question number one. In question number one, we have Kerr effect, but here we are considering chi2. Sorry, okay, you have one query. The curve is the broadening. The broadening refers to increase in delta omega, right? Okay, chirp means there is a variation of frequency inside the pulse. Okay, so that is what we mean by chirp. Like if the frequencies are decreasing, then we have a negative chirp, and if the frequency is increasing, then we have a positive chirp. Broadening itself means there is the width, the temporal width, as well as the spatial width. These are changing. So, if you recall in the class, whenever we have a nonlinearity, so the envelope looks similar, but there is a change in the phase, right? So there is a change in the instantaneous frequency. So that is why we say because of the nonlinearity, we are seeing the change in the phase and the change in the pulse. Broadening itself means delta omega, but when you are right, it's means broadening means delta omega. But when we have a sign like when delta omega is positive, then we can say this is a positive chirp, and when delta omega is negative, we can say this is negative chirp. So this is just a definition, the terms that we're using. So if I say so whenever there is a broadening non-linearity, you can recall the lecture. So before the center, the frequency is quite low, but after crossing the center, the frequency increases. So we see that even inside the pulse, there is a variation of omega. Okay, I think this is clear then. Okay, let us move to our next problem, which is related to the some frequency generation. Please go through the question once. So the question says consider a some frequency generation with wavelength of 2 micrometer and 1 micrometer. What is the wavelength of the generated wave because of this some frequency generation, and write the corresponding phase matching condition in terms of refractive indices at different wavelength. So if you recall, only when we have the required phase matching condition, then only we can see the optical Kerr effect or the frequency generation because of the nonlinearity. So it requires phase matching. For some frequency, what we need. So let us see the second question first. What is the phase matching condition for that? And so the process of some frequency is like this. Whenever we have a photon with frequency omega 1 and a photon with frequency omega 2. So this, whenever if the non-linear medium, this is a non-linear medium. So if the nonlinear medium satisfies the phase matching condition, then we'll see omega 3, which is summation of omega 1 plus omega 2. So this is the sum frequency generation process. So for this, what we need the phase matching condition. So let us say this omega 1 has the wave vector k1, and this has wave vector k2, and the omega 3 it has the resultant wave vector, which is k, or let's say k3. So the phase matching condition says k3 should be equal to k1 plus k2, so that we can see a some frequency generation. Okay, so if you write it down in terms of wavelength and refractive index, we know that k3 you can write it as k0 times refractive index. So that means this is nothing but 2 pi over lambda 3 n3, and this is 2 pi over lambda 1 n1 plus 2 pi over lambda 2 n2. 2 pi will cancel. So we have n3 lambda t n1 by lambda 1 plus n2 lambda 2. So this is the general expression for phase matching condition. Okay, so that means we know what is the answer to question, sorry, the second part. For the first part, to find out what is the wavelength of the some frequency generation, because it it's not given. The dependence of refractive index over wavelength, it's not given here. So what we can assume? We can assume that there is no dependence of refractive index for wavelength for the time being. So if it is given in the question, we can consider that. But if not, we can assume n3 lambda 3 equal to n1 lambda 1 equal to n2 lambda 2. So that means we have the phase matching condition 1 by lambda 3 should be equal to 1 by lambda 1 plus 1 by lambda 2. Lambda 1 and lambda 2 is already given in the problem. So lambda 1 is 2 micrometer and lambda 2 is 1 micrometer. So this is 1 by 2 plus 1 by 1, which is 1.5, right? So lambda 3 will be 1 by 1.5. This will come around 0.666 micrometer. So this is for the sum frequency generation, the phase matching condition for the sum frequency generation. So is this clear to you? Okay, so then we'll move to question number 8. Now go through the question once. So there is a wave corresponding to frequency omega 1 and omega 2. These are launched into an optical fiber, and the question is asking about obtain the expression for the nonlinear polarization at frequency omega 3, which is equal to 2 omega 1 minus omega 2, and what is the velocity of the nonlinear polarization at omega 3. So the question is asking, for the first part, it is asking what is P and N corresponding to omega 3 is equal to 2 omega 1 minus omega 2. Next part, it is about calculation of its velocity. So if you recall the first question, in the first question, we have an expression like this only. The electric field has two frequency. One is omega 1 t minus beta 1 z plus E2 cos omega 2t minus beta 2z. So I'm just writing the expression that we got before. So EQ in the problem we have seen this, we can write it as 1 by 8 E1 e to the power I omega 1 t minus beta 1 z plus E1 star e to the power minus I. This term we have taken it as the term A, and there is one term which is E2 e to the power I omega 2t minus beta 2z plus E2 star e to the power minus I omega 2t minus beta 2z. This we have taken it as B whole to the power Q. But in the first problem, we were interested in the terms which has omega 1. And for this problem, we are interested in the terms which is 2 omega 1 minus omega 2. So let us see. So EQ ZT is 1 by 8. Is there any rule about when it is better to use complex representation and when it's better to use? Okay, you are asking about in which situation we can use the complex representation and in which situation we can use the cost function. Okay, so it's totally depends on the for this course. It's for the exam purpose. We I can say it's all depends on the answer. So if you look at just look at the before solving the question, just look at the answer, how the answers are like. So if it is written in terms of complex conjugate, complex representation, then it's better to take the exponential form. But if it is written in terms of cos and sine, then it's better to use that. And for a real life problem, it doesn't matter because they are equivalent. Okay, for more realistic purpose, we use only the cos part because electric field is nothing but the real part of the exponential. So in the experiment, we see only the real part. So that is why for this, I can say just look at the answer, how the answer is like in the question. If it is in terms of exponential, just use the exponential form, or if it is in terms of cos and sine, you use cos and sine. Okay, so this we have already seen before. So just make sure while doing this calculation, because you can see these are really, really long calculation. Like there are lot of terms here. So your first, so you just need to look for the terms that will have the frequency component that the question is asking about. For this question, we are interested in looking at the term with omega 1 minus omega 2. Okay, so that is why you don't need to expand all the terms. Just look the terms which will have this frequency. So for before that, let me write down what is A. A is E1, E2, I omega 1 t minus beta 1 z plus E1 star e2 r minus I minus beta 1 z. So this we have already seen before. Okay, so let us see the terms we are interested in is omega 3, which is 2 omega 1 minus omega 2. So A plus AQ term, let us see the AQ term. So AQ term means volt over Q. So this term will don't have any component of omega 2, right? Because it is all in omega 1. So that means it doesn't have any omega 3 term. Similarly for BQ, BQ also it has only omega 2 term. So that means it doesn't have any omega 3 term. Now let us see 3a square b. So if you roughly see it, the first term here, it will give a square will give 2 omega 1, right? And if you multiply with the term, not this term, the second term of this will give 2 omega 1 minus omega 2. That means 3a square b will give a term like omega 3. So let us see the details of the terms. So first is by multiplying 1. So let us, okay, this is 1, this is 2, this is 3, and this is 4. So if you multiply 1 with 4, we'll get, so we have to take the square also because it's a square b. So, okay, 3. So let me write it in detail first. B1 z plus E1 star e to power minus I B1 z whole square b. Okay. So now if you multiply the square of the first term with the fourth term, so this is 1, 2, 3, and 4. So if you multiply 1 with 4, we have a term like 3 e1 squared e2 star e to power I 2 omega 1 minus omega 2 t minus 2 beta 1 minus beta 2 z. Now, for the, so we have seen a square. Now, if you take the square of second term and if you multiply with the third term, so if you multiply 2 square of 2 with 3, so this will give 2 omega 1. There is a plus omega 2 here. So we'll get 2 omega 1 minus omega 2. So E1 starts with E2, E2 are minus I 2 omega 1 minus omega 2 t minus 2 beta 1 minus beta 2 z. So this 3 a square b will give a term like this. For 3ab square, so we have 3ab square. So that means this is 3 multiplied with e1 e to power by omega 1 t minus beta 1 z plus e1 star e to power minus I beta 1 z multiplied by square of omega t minus beta 2 z plus e2 star square. So we need term like 2 omega 1 minus omega 2. But in the term you can see the square part. So this will give 2 omega 1, and if you multiply with the first term, it will give 2 omega 2 minus 2 omega 2 plus omega 1. And if you multiply with this term, it will give 2 omega 2 minus omega 1, which is not, we don't want that. Similarly, the second term will give omega 2 minus, sorry, 2 omega 2 minus omega 1, and 2 omega 2 plus omega 1, and 2 omega 2 minus omega 1. And there will be a DC term also, which will have e square, that is e2 square. But if you multiply e2 square with the first term and the second term, there is no term will give 2 omega 1 minus omega 2. So this will give omega 1 only. So that means 3a square b doesn't contribute to the nonlinear polarization due to omega 3, which is 2 omega 1 minus omega 2. So only this component, which is 3a square b, it has the term which is due to 2 omega 1 minus omega 2. So now finding the nonlinear polarization is easy. So we just need to multiply with epsilon chi 3 by 8, 3 e1 square e2 star e2 r I omega 3 t minus 2 beta 1 minus beta 2 z plus 3 e1 square e2 e2 r minus 9 omega 3t minus 2 beta 1 minus beta 2. Okay, so this is for the first part of the question. In the next part, problem was asking about what is the velocity of this nonlinear polarization at nonlinear wave at frequency omega 3. So can you let me know what will be the answer like? So you have a nonlinear polarization like this. Now you need to find out what is the velocity due to the omega 3. How you can calculate it? So to calculate it, so you know the electric field expression, right? For omega 3, only the 3a square b part will have uh, the term which is due to the omega 3. So just look for what is the value of omega and what is the value of k for this case. So omega for this situation, omega 3 is omega 3 and k is 2 beta 1 minus beta 2. So that means the velocity, it is nothing but omega by q. This is omega 3 minus 2 beta 1 minus beta 2. So is this clear? Okay, so let us move to our next problem. So it's based on the nonlinear refractive index change. What is the susceptibility? Okay, let me read out the question first. So there is one optical fiber which is the following parameter, like the linear refractive index, which is no nonlinearity. It is given 1.45, and the nonlinear refractive index coefficient, it is also given, which is N2 is 2.5 into 10 to the minus 20. So we are launching a laser beam at wavelength 1550 nanometer, which propagates with the fiber with intensity I is 10 to the power 9 watt per meter square. So the first question is you need to find out what is the linear susceptibility of the medium and what is the nonlinear such a susceptibility due to the Kerr effect, and compute the effective susceptibility and find out the total change in refractive index due to the self-phase modulation. So finding the linear susceptibility is it's easy because already the linear refractive index is already given. So if you recall the lecture, so n0 you can write it as square root of epsilon r, or it is square 1 plus the linear susceptibility, which is the first chi1 component. So that means we have 1 plus chi1 is n0 square. So the chi1, it is nothing but n0 square minus 1. So this is the linear susceptibility, and n0 is 1.45. So this will give 1.1025. Okay, the first part is done. So in the next part, we need to find out what is chi3 due to the Kerr effect. So for chi3, what we need, if you recall, n is n0 plus n2 into I. N2 is, it is related to the chi3 by the expression n2 is 3 chi3 by 4 n0 square epsilon naught c. So chi3 is 4 n0 square into epsilon c by 3. All of the parameter is already given in the question. So finding the chi3, it's straightforward now. So okay, 4 epsilon naught is 8.85 into 10 to the minus 12. C is 3 into 10 to the power 8 meter per second. N0 square is 1.45 square, and N2 is what is N2? 2.5 into 10 to the minus 20 by 3. So this will give 1.86 into 10 to the minus 20. This is the chi3. Now for the third part, we need to compute what is chi effective because of the non-linearity, which is also straightforward because chi effective, it is related to the linear susceptibility plus 3 chi3 2 epsilon naught n0 c I. Chi1 we have already calculated. So chi1 was 1.1025. So this will be, so chi effective will come around linear susceptibility because this term it's nearly negligible. So 3 chi3 is 1.86. I, it was given 20.9, I think. Yes. N0 is 1.45 and we have 3 into 10 to the 8. So this will give 1.1025 plus 0.0725 into 10 to the minus 7. So this is almost equal to 1.1025. So this is the effective susceptibility. Now for the change in refractive index, which is also straightforward because you have the N2 term and you know the intensity. and delta n is nothing but n2 into I. So we have the change in refractive index. It is n2 into I. n2 is 2.5, 10 to the minus 20 into 10 to the 9. So this will give 2.5 to 10 to the minus 11. So this problem was based on the formula. Now we'll see our next problem, which is a bit different. No, it's I think it's easy. So can you go through the question and let me know the answer? The question says consider a mode carrying 100 milliwatt of power in a single mode fiber with a effective area of 50 micrometers square. Calculate the change in refractive index due to the nonlinear effect. And N2 is also given. It is 3.2 into 10 to the minus 20. So power is given 100 milliwatt and the effective area is also given. It is 50 micrometers square and N2 is given. So what will be delta M now? Yes, it is N2P by A effective, which is easy to calculate. It is 3.2 10 to the minus 20. This is 0.1 and A effective is 50. So this will give 6.4 into 10 to the minus 11. You will see in the next lectures that even though there is a this value is very small, right? Delta n is it is in the order of 10 to the minus 11, which is very small. But if you consider a length, like if the interaction length of the fiber, it is of the order of 10 to the 4 kilometer or 10 to the 5 kilometer, you can see this factor, this delta, the total change in refractive index will be significant in that case. And this small value of delta n, it is responsible for formation of soliton. So that we'll see in our next lab section. Okay, so let us move to our next problem. It is this is a bit different to what we've seen earlier. Some of them are straightforward, but some of them require one additional information. So let me read out the question. So there is a Gaussian pulse with the electric field given by E z equal to 0 t. It is E0 e to the minus t square tau 0 square e to the I omega 0 t. It is launched into the fiber and the fiber is the following fiber parameter. It is given the wavelength of operation is around 50 nanometer, which is the low frequency window of the communication. So lambda it is 1.55 micrometer. N2 is given 2.6 into 10 to the minus 20. And A effective is also given. A effective it is given 80 micrometers square. And the group velocity is also given. It is 2 into 10 to the 8 meter per second. And the Gaussian pulse has a pulse width of tau 0, which is 8 picosecond, and the peak power corresponding to this pulse is P0, which is 5 milliwatt. So in the first part of the question, we need to calculate what is the nonlinear coefficient gamma of the fiber. And in the second part, we need to calculate what is the nonlinear phase shift of the pulse center after propagating a distance of 10 kilometers. And in the third part, it's a situation where we need to find out what will happen if the pulse width, if we doubles the pulse width due to the dispersion, then how does this affect the peak nonlinear phase shift? So let us see the A part first. So for A, we need to find out what is the value of nonlinear uh, coefficient. So gamma, it is nothing but, if you recall, this is into K0 by A factor. K0, you can write it as N2 omega 0 by C A factor. And omega 0 is nothing but 2 pi C over lambda. So let us calculate omega first. So omega 0 is 2 pi C over lambda, which is 2 pi. C is 3 into 10 to the power 8. And lambda is given 1.55 micrometer. So this will give a value of 1.215 into 10 to the power 15 radian per second. So omega 0 we know. Now let us put it in gamma. Gamma is into omega 0 C A effective. N2 is 2.6 into 10 to the power 20, and omega 0 is 1.215. C is 3 into 10 to the power 8, and A effective is 80 micrometers square. So this will give a value of 1.316 into 10 to the power minus 3. So in the second part, we need to calculate what is the nonlinear phase shift at the peak center. So nonlinear phase shift at the pulse center. So phi, you can write it as gamma pt into z, and pt, if you recall, we have expression pt is p0 e to power minus 2t square by t0 square. So this is the expression that has been derived in the lecture. And we want the nonlinear phase shift at the pulse centers. That means the PT, the pulse center, it is maximum, right? It is equal to P0. So now we have gamma NL. It is, sorry, phi NL is gamma P0 Z. Gamma, it's already being calculated. It is 1.316 into 10 to the minus 3. And P0 is, it's already given, 5 milliwatt. And Z, I think, 10 kilometer, right? So the phase shift will be 6.65.8 into 10 to the minus 3. So this is the phase shift at the pulse center. Now for the C part is telling, now we have a pulse width like T0. Now we are increasing the pulse width to 2 times of T0 or tau 0. Then how will this phase shift will get affected because of the change in the pulse width? So we are changing tau 0 to tau 0. Then how will be pi nm? Do you know the answer? How you can approach this? Just look at the expression for phi NL. How does the phi NL depends on the tau 0? This is tau 0 only. If you're taking T0, then this is T0. Recall PT is P0 e1 minus 2t square by T0. This is tau 0 square. Okay. So if not, so let me. So it will be the power becomes half of the initial value. How? Because if, whenever the pulse is propagating, there will be conservation of energy, right? So we need to apply that. So even though the pulse broaden, their energy will remain conserved. So let us say we have initial situation, we have power PT is P0 e to power minus 2t square by tau 0 square. So what will be the energy expression for this? Energy is nothing but integration of PT dt, right? So this will give P0 e to power minus 2t square by tau 0 square into dt. So this will give P is 0 square root pi tau 0 square by 2. So this is before broadening, we have energy like this. Now, because we are increasing the temporal width, we have a power PT, which is P0 prime e to power minus 2 t square over tau 0 square will be 2 times tau 0 square. So that means we have now the energy. It is nothing but E0 prime minus infinity to infinity e to power minus 2t square by 2 tau 0 square. So this will give, the integration will give t0 prime square root uh, 2 tau 0 pi, 2 tau 0 square pi. So energy will be conserved either before broadening or after broadening. So you can equate this two. So that means P0 tau 0 square root pi by 2. It is P0 prime tau 0 square root 2 pi. This will cancel. So we have the P0 prime, which is half of its initial value. So power will be, the peak value of power will decrease to half of its initial value. So this is only for the case when we are increasing the temporal width to 2 times of the initial width. If you have a situation like, and you can easily calculate, just use the energy conservation rule. And now finding out the phi NL is easy because phi NL at the pulse center it is gamma P0 prime Z. So gamma P0 Z by 2. So that means this is half of its initial phase set. Okay. So do you have any query till now or in this problem? Otherwise, we'll solve our uh, last question. Okay. If not, then let us see. Last problem. So there is an optical pulse, which is the expression it is E0 e to power minus t square by tau 0 square e to power I omega 0 t. It propagates in a nonlinear medium with the wavelength of operation. Lambda is 50 nanometer. And 2 it is given 3 into 10 to the minus 20. And what else? A effective is also given. It is 50 micrometer square. The peak power is 10 milliwatt and the temporal width is 5 picosecond. So in the first part, we need to calculate the nonlinear coefficient of the medium, which is gamma, right? So we need to find out what is gamma. So if you recall the expression, gamma is nothing but N2 omega 0 by C A effective, which is N2 2 pi C over lambda A effective. So this is already given. N2 is 3 into 10 to the minus 20. And lambda is also given. It is 50 nanometer and A effective is 50 micrometer. So we have 3 10 to the minus 20 2 pi c lambda is 1550 10 to the minus 9 and 850 is 10 to the minus 1250. So this will come around 2.43. So let us see the B part. For the B part, we need to find out what is the maximum nonlinear phase shift occupied by the phase at a distance after traveling a distance of 5 kilometers, which is also easy to find out because we have seen the expression of maximum phase shift. So phi maximum will be at the uh, pulse center. So this is gamma P0 Z. So gamma is 2.43 and P0 is 10 milliwatt and this is 5 kilometer. This will give 0.1215 radian. Okay, so this is for the B part. In the C part, it is asking what is the expression for the frequency shift as a function of time, which it's already been in the lecture. So delta omega T is 4 omega 4 gamma P0 Z T by T0 square e to power minus 2 T square by tau 0 square, where T is or T prime you can take. Let us take T prime. T prime is T minus Z minus Vc. You can see in the expression delta omega, it is directly proportional to T dash, which is T minus Z minus Vc. So in the D part, it is asking so that the leading is has a negative delta omega and the trailing is it has a positive value of delta omega. So negative delta omega means there is a negative chirp in the pulse and positive means it's a positive chirp. So this is also straightforward because we already seen the expression that is delta omega t prime. It is directly proportional to t minus z minus phase. So for the leading is we have t is less than z minus phase. So for this case, we will see delta omega will have a negative sign. And for the trailing is that is t greater than z by bz, we see that delta omega will be positive. So delta omega is negative means, as I have said before, if it is a envelope of the pulse that is propagating inside the nonlinear medium, then when delta omega is negative, that means the frequency will decrease. So that is why we'll see a decrease in the frequency. Decrease in the frequency means increase in the wavelength, right? Okay, that. And for the trailing is we have delta omega, it's increasing. Its positive sign means it is increasing. So we'll have frequency component that is closely separated, closely placed to each other. Okay. So for this case, there is another term also. This is where we are seeing there is a decrease in the frequency. That means the wavelength is increasing. So we'll see a rate shift here. And for this reason, there is a increase in the frequency. So that means the wavelength will now decrease. So there will be a blue shift. So these are terminology, different terminology that is used, or this reason correspond to negative char because delta omega is negative, and this reason correspond to positive char. Okay. So this is all about the problems that I wanted to solve, which mostly covers the concept related to week 11. Uh, Let me ask if you have any other doubt regarding the lectures or regarding any doubt in this problem. Let me ask, or will so I will not be able to attend the next live section. Okay, so I guess the next live session is the last. Yes, next live session will be the last live session. So I will ask this question outside. How will be the final exam? Is it enough to practice using assignment and problems in solve in the live session? Okay, so generally the NPTEL exam it's like it has three question types. One is if I remember correctly, so there will be MCQ type, and there will be problems that will ask. So the parameters will be given, and you will be asked to find out what is the answer for this. Like what is the gamma of this fiber, not in case of Kerr effect. So that is one type. Like fill in the blanks. Like you will be given the parameters, and you need to find out other parameter. That is another type, and two of they two is MCQ type and one is this type where you need to calculate it to find out the answer. So regarding whether it is enough to practice using assignment and problem solve in the life system, yes. It's really it's if you go through the lectures and assignment. So just don't look for only the assignment as well as the problem solved in the live section. So go through the concept whatever there in the lecture. Maybe some of the concept hasn't been asked in the assignment. So go through the lecture slides, all of the slides, and all the question of the assignment, the weekly assignment, as well as the problems that I've solved in the live session. This is enough for you to tackle the exam. Please say the tutorial slides or at last the PDF of all the tutorial. Okay. I think up to week 7, I have shared all the slides. I think from 8, I haven't shared it. So I will share it by tomorrow. It will be uploaded in the Google Drive link. So please wait for tomorrow. Okay, any other doubt we have? So Niranjan, I think I have clarified your doubt, right? Okay. Okay, so thank you for joining the live section. Will please, if it is possible, please try to attend the last live section, which will be on Monday from 6 to 8. So we'll solve some additional problem related to optical soliton, as well as some problems that covers all the concept. Okay, so thank you for joining the live section. We'll meet on next Monday. So goodbye everyone.